So now we're going to look at two types that are very common in functional programming, lists and binary trees, especially lists. So lists are really all over the place. And they're also all over the place in proving. So when you're proving in Lean, you often need lists, especially for computer science-oriented applications, but even for mathematics, lists are quite useful. So we remember what a list was. We had two constructors, nil and cons, the empty list and the list that adds one element at the front. And that one has this, I mean, both of them have special syntaxes. And one of the things we can do that's illustrated here, I'm going to show lots of things that can be done with lists. And also some of them are, more generally useful for all data types. So the first thing I want to show is a special use of cases, right? So before we saw our cases prime, it's always with prime. So earlier I showed how you could use cases on a value, right? So a value of an inductive type or a structure. So you can also do a cases on a proof, so on an assumption, for example. So we can say cases of the assumption H, right? And what this does in some sense is destroys here the equality. It extracts the reason why we could say that these things were equal. And in this case, it says, well, the only way this cons could have been equal to that cons is if x equals y and xs equals ys. So it does that substitution for us, right? So we started with a goal that says x equals y, xs equals ys. And we say, well, let's try to exploit this equality up there. And then we end up with something completely trivial where x equals x and xs equals xs. So of course I could here use and intro, obtain two sub goals, and then use refl on both of them. But I'm just going to kill it with cc. I wonder, simplifier, can it do it? Simplifier can also do it. But cc is less typing and it's the same key twice, right? So it's very convenient for the finger. Just have to hit the right one. Okay. And this is another example which is similar. So here this was in injectivity. So you had twice the same constructor, and then Lean is smart enough to know, well, the only way for for the arguments to be for the values to be equal is for the arguments to be equal. But sometimes you have something that is disequal, and here I'm using the syntactic sugar for cons and the syntactic sugar for nil. So this is simply impossible here. So what I do here is I do a case distinction on that, and I say, under which conditions can nil be equal to cons? And then Lean pops up exactly 0 sub-goals, because there are 0 cases where this can happen, and that closes the proof. So I just do that. That's distinctness of the constructors, or the no confusion property, if you prefer. Okay. This is a map function. It's a very common function on lists. You have it in Lisp, you have it in Haskell, you have it everywhere. You have it in MapReduce from Google. That's the map. And it's also called a functorial action, I think, in category theory. It's really a very important concept because it lifts a function from alpha to beta into a function from list alpha to list beta, right? So it just elevates it so that it applies it pointwise, right? So you have a function you want to apply to all elements of the list. You can use map to do that. So for the empty list, it does nothing. And you see for a cons, then it applies the function on the head and it continues recursively. And you see we don't pass f here because f is a parameter. It's on the left-hand side of the column. So it's fixed for the entire definition. But later when we'll use map, then we'll need to pass it. And this is the alternative definition where we move this argument on the other side. And then we also need to do pattern matching on it, and here the f appears. And here in the recursive call, then we have to specify it because it's no longer fixed, right? And well, this is just a reminder that map, of course, already exists in Lean, so don't use this definition, just use the standard one if you need anything. And this is an example of a lemma we might want to prove about map, which is that if you use the identity function as argument and you map and you apply that to all elements of your list XS, then that will do nothing. You will end up with the same list that you started with, right? So we do the induction, we end up with 2 cases, right? The nil case here is trivial. We can, I mean, what does it look like even? It just says that map of a nil, and of course this goes straight into the first equation here and is game over. And for cons, well, it's still fairly easy because we have the induction hypothesis here to help us. So map of a cons, the simplifier will break that apart, and then we'll have something that matches. I mean, I could do it in 2 steps if I wanted, right? So we could start like this, right? It already did a lot of simplification, and then we're we just have to apply the. We could even write the assumption here, and it would be done. Okay. Another nice property, which is if you have 2 maps in a row, you map F, you map G, well, you can map their composition, right? So this is the composition of G and F, right? So it's, in mathematics, it's often written G circle F, right? And I wonder if Lean parses it, and indeed it does, so that's the same thing again. Wasn't sure for a second. But let's use the lambda version, because here we see we get an argument, we pass it to F, then we pass it to G. So there's no ambiguity, we know in which order it goes. So you're right, we show that we can compress 2 maps into one. And you know, again, it's the same proof actually. It's literally the same proof, it's copy pasted. Map append, another property. And again, it's literally the same proof. Because it's just a very straightforward proof where all you need is the induction hypothesis and the definition of map. So that's how it goes. Okay, we define more functions. We're going to define quite a few functions. They will eliminate various aspects of list, but also you know, of totality here below. So you know, questions such as you know, what's the result of division by 0 and things like that. So let's start with tail. So what is the tail of a list? Well, that's easy if you have a cons, right? You just return XS. But if you have a head, then, not a head, but an empty list, then you could say, oh, I don't know, it has no tail. The empty list has no tail. But that just causes problems, right? Because that's a partial function, and then, you know, how do we deal with this? Or, you know, do we, I mean, I'm going to show later how to do it, but you know, typically in proof assistance, if there's a nice default value we can give, then we give it, right? So the tail of the empty list is the empty list, is the empty list, is the empty list. That's a good default. It's very reasonable. So we're going to choose that, and that makes the function total, which is you know, always good. And again, I'm just pointing out there exists a function, you know, that is defined in that way in the official library, and they also made the same choice of returning the empty list. Other proof assistants do the same. Isabel does the same. Now comes the really interesting function, the head function, right? Because we already saw one solution to the head problem, which was we're just going to require. I mean, you recall that we didn't know what to return in the nil case. And we just, you know, above we, well, I can go there, right? We just use inhabited and we return the default. But this is not the only option. And actually, one of the options is to use an option, no pun intended, or maybe yes, is to use the type option, which has 2 constructors, none and sum. So sum is just a little wrapper for value of type alpha, and none adds an extra value, right? So if you were programming in C or C++, you would probably be returning -1 to say, oh, this is a special value, there was an error, and so on. With option, you just return none, And if everything went fine, then you return sum with the value you wanted to return all along. So here, this is what we do. We return none in this case, and we return sum in the other case. This is very clean, but it's cumbersome because you have then to do a case distinction, on the result. Is it none? Is it sum? You might just as well, check if the list was empty or not, if that bothers you. If this case bothers you, just check ahead of time that you're not calling the function on an empty list, all right? Okay, so that was, I would say this is not a very interesting solution, but it does the job. It doesn't require inhabited, which is already a, maybe you have an inhabited type which is not registered, and that's a bit clumsy, or this version doesn't suffer from that flaw, so it might be good. There's another version which is perhaps the best in a proof assistant that supports dependent types. It's to have a precondition on your function. You say, well, you're allowed to call head, or head LE as it's called here, at the condition that you also give me a proof that your list is not empty. All right, so it's quite hard to parse, even for me, I must say. So here what it's saying is, okay, we take a list as argument, and we take a proof that that list is not the empty list. And then I can return an element of type alpha, right? So this is the novelty here, right? So if we have the empty list and we have the proof, right? Then we end up in, let's say, this situation where we have list nil different from list nil. I could do a cases here on this thing. I think that would, oh no, it's a negation. So, right, so it's a bit tedious. So that's why I just wrote by CC. I didn't want to wonder, okay, how am I going to do this proof? It's, these silly little things that look a bit nasty, you can give them to proof automation and just move on. And otherwise, the head is, of course, just the X there. Okay. And now this is how we use these different functions. So head up here, right? On 3.14, return sum tree. Here, the other version with a proof as argument. Also returns tree, but you need to prove, you need to pass a proof here, which here I just proved by simp, right? So I just entered tactic mode and proved that this list is not empty. But then if we try, this is interesting here, because here I passed the empty list, and I was very mean. I didn't really pass a proof. I passed sorry, which I shouldn't have done. So it's like, and then I'm like, okay, what will happen? And I was very curious to see what happens. And it says VM unreachable instruction has been reached. So I don't know if that was intended, but it's basically not good. It's a sign we shouldn't be doing stuff like that, right? So those were the different strategies that could be used to define partial functions. So head is a really nice example to illustrate all these strategies. Okay, so let's see, where's my water? Another function called zip, right? And here I was very careful to define the patterns so that they don't overlap. So we have the case const, we have the case nil anything, and we have the case const nil. So everything, there's only one case that can happen for any combination of nil or non-nil list. And whenever one of the two lists is empty, return empty. I mean, I should say zip just takes two lists, ideally of the same length. We have the x's on one side, the y's on the other side, and then you create a list of pairs, right? So you put the x with the y here at the head, and then you continue recursively. So this is a very useful function in functional programming. And we see lean also has such a function. Here you have the length function. This is one of the most straightforward one and also exists in Lean. All right, so very simple recursion. So we've seen two uses of cases or cases prime so far, and now I'm going to show a third use, which it's an idiom really. So it's just a special case of things we've been doing before. So let's see. Where is it? There it is. There it is. And there's a really weird comment here, which I'm going to kill. I think the half tactic doesn't exist anymore. So I'm going to kill that so that you are not confused later. Okay. Not seeing any halves below, so I think we have halves nuts. So the idiom is based on, I mean, sometimes in the proof we want to do a case distinction on the truth value of something, right? So if P is true, then you want to go one way, or otherwise you go another way. So if N is greater than 5, you do something, otherwise do something else. And this can be accomplished in a number of ways in Lean, but the simplest one, given the tools that we have, is to use cases prime in conjunction with classical M excluded middle, which we've seen. So these, we're just going to combine two ingredients that we already know, and we'll be able to do something quite cool with them. So excluded middle says that for all P, either P or not P, because we work in a classical logic, which is, this is an axiom, we've just decided that, or somebody has decided for us that this is how things are in Lean. And here you see have a property about min, about the minimum. We're trying to factor out this L here and move it over there. And the first thing we want to know is whether M is greater or equal N or not, because the definition of min has exactly this less or equal there. And then depending on the case, we're going to be able to get rid of the if and just have the A and or the B, so the body of the function, right? So we do a case distinction here. And the case distinction is really a combination of things we already know. So we have a property here, and then we tell classical EM, create a proof, of P or not P. This is, what it does. And then we do a case distinction on it to say, either it's P or it's not P. And well, the labels are, a bit unfriendly here. But this means left, that's the L, and the other one means, so it's the left of OR, and this is the right of OR. So in the case where, this condition is true, then, well, in that case, we just use the simplifier, and that does it. But it also needs the hypothesis that M is less or equal than N. This is what allows the simplifier to simplify the if then else to take the left branch. And here it's exactly the same thing again, but this time we take the right branch. And so this is how it works. Of course, we could do the proof here like in smaller steps, but the important part is here. This idiom is just a case distinction, true or false on this. And I should show here, you see, in the false case, you have the hypothesis that it's false, so, which you can use. Okay. And if you prefer match to cases prime, then this is the version that does the same. So you can also do a case distinction here on the constructors of the OR, basically. And this is yet another version. So instead of a match, we can, or instead of match and classical EM, if we're doing structured proofs, then we can use an if then else. And we can give a name here to the hypothesis, and in the else case, then the name is used for the negation of the hypothesis. So this is a shorter version of that, but and it has the advantage that it reuses things we know. So we see if then else can be used not only in programs, but also in proofs. And the same thing with match, by the way, right? And this is possible thanks to Curry Howard, as usual. Right, so we're getting close to the end of lists, I believe. This is another proof that's a bit longer. Just, I think this is one you can look at home if you want, and try to remove some bits and try to find it if you want as an exercise. It's once you have defined length and you've defined zip, you want to, and in min, then you want to prove a property that combines all three, right? The length of the zip is the minimum of the lengths of the list, right? So that's these kind of properties are very useful. As soon as you have two operators and they can interact, then you probably want to prove a lemma about them. It's going to be useful if you build a big library based on that. And here, this is the interactions between map and zip, right? So which is a rather complicated property with an easy proof in the end. And notice that the proof follows exactly the same pattern as the definition of map. So you have the same three cases, and two of the cases are very easy because that was just the empty list. And this one is actually not very hard. Although when you develop the proof, typically you'd have several steps, and this is what happens when you compress it at the end. But what this is saying is, if you apply the map on the zip, you can also have the zip of the maps, right? So you can commute the two in some sense, which is made clear here. But yeah, this one is a bit more tricky. I'm not going to ask you to write ugly stuff like that at the exam, don't worry. Okay, I'll move on to the binary trees because I know I've been talking for quite some time about lists, and if you want to press pause here for 5 minutes, I would understand. But I'm really not going to spend much time on binary trees. Let's see. So binary trees can be defined in various ways. There's no canonical binary tree type, let's say, but this one is pretty close to it. So it's polymorphic, right? So it has a parameter of type alpha, has the empty case. You can ignore these braces for the moment. They're explained, I think, in the guide. And you have a node which is labeled with alpha, and it has two children, right? So you either have empty trees, completely empty, or you have binary nodes with alpha. Maybe I can do a little drawing if I find. Let's see. Need to make a bit of space on my whiteboard. So something like this. So something like this would be a binary tree. So the X's at the bottom, the three X's, those just indicate the empty nodes. And then the real nodes, which are called node, have a label on them, which I called A and B, of type alpha. Okay. Right. So now what's going to be interesting about this type is that you have two occurrences here, recursive occurrence of itself in the argument. So that means you're going to get two induction hypotheses instead of a single one. It's not much different from lists, but that's a new thing. And the example we use is mirror, which is a bit like reverse. So it flips a tree around. So the empty tree is the empty tree. And if the node is LR, has children L and R, then you take the mirror of R and the mirror of L in that order, so that you swap recursively, but you also swap, at the level at which you're looking at, and you keep the label intact. And then, the first property you want to prove is, of course, that mirror of mirror is the original tree, because, that's what you want to do with mirrors and reverse and so on. And the proof is fairly straightforward. It's actually easier than for lists. And you see, but you see that you need both induction hypothesis here. So if you look at the state in more detail, you're going to see that, well, let's just do it. We're going to see, okay, where are we at? We have mirror L equals L and mirror R equals R, and those are exactly the two hypotheses. So I think this is where we could just call CC if we wanted. All right. But it's always nice to put the induction hypothesis explicitly at the places where you use them. That really serves as documentation, so I prefer to do that. This is a calculational proof, right? Which we use once in a while. So sometimes when, if simplifier is nice, it does lots of things for us, but, sometimes it goes out of control and we would like to do things in small steps and know what we're doing. This is when calculational proofs are really good. So here I've done it really step by step, one rewrite or one operation at a time until I ended up with what I wanted to prove, right? Which is that this thing equals that thing here, right? And yeah, this is another property that about emptiness that's very easy to prove. And that completes a very brief review of binary trees. I just wanted to show that lists are not the only data type, so to speak. And that concludes the lecture for today. There is a bit of material left in the file, but you see it's marked as optional. And well, this is covered in the Hitchhiker's Guide. It's about dependent inductive types. So for example, here you have the vector type, which is a bit like a list, but it carries its own length. So you can say, I have a vector of length 3, right? So const will take a vector of length n and return a vector of length n plus 1. So you're really deep into dependent type theory at this point. And yeah, these types are not so friendly. They don't work well with automation. You get you get type errors more often than when you don't use them. So it's generally not recommended to use them. There are usually better approaches. For example, here for vectors, a better approach generally is to just take a type of list and to pair it with a length. And that's something we're going to learn to do in lecture 11, I think. But basically, the advantage then is that we reuse lists, we reuse the rich list libraries, as opposed to creating a new type vector, which has then we have to rebuild, all the operators, the zip, the map, the everything, instead of just reusing them. So this is entirely optional, and if you're curious, you can read about it. One reason to read about it is that if you understand this material in the guide, then you will understand a bit better what happens in the next lecture. So I'll do my best to explain it well there, but there's a kind of Curry-Howard bridge again, and it one side of the bridge is dependent inductive type. So if you know that side well enough, then when you come on the other side, you're going to have an advantage over those who haven't. But regardless, you're going to find next lecture.